Newton's laws are one of the most important things that we learn about forces. And again, forces are a push or a pull. They're measured in newtons. Which we abbreviate as a capital N. They are a vector, which, if you remember the difference between vectors and scalars, a vector has both a magnitude, a size, a number that goes with it, and a direction. Now, these are our first named unit, newtons. They're named after Isaac Newton, who you've probably heard about before. He's the guy with the apple that fell, and he thought about why it fell. We actually talked about this apple last unit when we talked about gravity, which is also something we're going to come back to. And a named unit basically is when a unit, in this case, kilogram meters per second squared, is so complex that saying it over and over again would be really, really cumbersome. Kilogram meter per second squared, kilogram meter per second squared. It'd be a lot. And so what we do in this case is we make a new unit, and we tend to name it after somebody who did a lot of work in the field that we're looking at. And in this case, it's forces. And so the work that Newton did, it's not that people didn't understand before Isaac Newton that forces were a thing or important, but he put into words why they were important, exactly what they did, and how they worked. And he did this in something called Newton's laws. There are 3 of these. You've probably heard at least 2 of them before, but I want to make sure that we go over them again. And that part of that reason is because as we learn things and spiral back to things we've seen before, sometimes we add a little bit of complication, because as you get older and as you get more mature as a scientist, you're more able to understand some of the complications. So we'll start with Newton's first law. And in Newton's first law, he said that an object in motion will stay in motion and, to be clear, an object at rest will stay at rest unless acted upon by some, and this is where we get to some words that are pretty important, net outside force. And these 2 words, net and outside, are words that maybe you haven't heard before when you've heard Newton's first law. So let's talk about each of them. I think we'll start with outside, because I think that one makes the most sense. You know, if you keep pushing yourself, you're not going to push yourself over. You know, you're not going to land on the ground because you were pushing yourself too hard. If you want something to happen, it has to have an outside force, not just something within the object itself. Think about like how you walk around all day and organs and things are doing their job. Lots of forces are happening inside your body and you're basically not even aware of it. And that's sort of what we've got going on here. Net is the other word here. And net, you may have heard before when it comes to things like a net salary versus a gross salary. Gross salary is like the total amount of money that your company says they're paying you. And they do pay you that. But one of the sad truths of adulthood is that before they actually give it to you in a check, they take away some money. And some of that money is for taxes, some of it's for your insurance, and so you don't get to take it all home. You only get to take home part of it. And that's what we call your net salary. And so the total amount minus other things that like get taken out is your net. Same way with forces. Sometimes when we look at forces, and by the way, you'll see a lot of these in this class. It's called a free body diagram. And it's just a picture of the object with any forces that are acting on it. So if we have a bunch of force, let's say 50 newtons worth of force pushing to the right, and 10 newtons pushing to the left, when we think about what this box is actually feeling, well, it's got all that 50 to the right, but about 10 of it is getting canceled out by being pulled a little bit to the left as well. And so the net force in this case, and by the way that we write net force is sigma F. This is a sigma, a capital sigma for the record. And in math, that means the sum of all whatever follows it. So we've got sigma F, the sum of all forces, which is the net force. And that is equal to all of the positive forces we have, 50 here, minus all the negative forces we have, 10. So here, the net force on that object is just 40 newtons. And in fact, we could even have net force where all of the force cancels out. Here, the net force is all the positive forces minus all the negative forces for a grand total of 0 newtons. So for an object to change its motion, and that means either speeding up and slowing down or even changing its direction, it has to have some net outside force. In other words, the forces can't all cancel each other out. There has to be something left over. We call this law, by the way, the law of inertia. And the word inertia just means that objects tend to want to move in the same direction unless a force gets involved. All right, Newton's second law is basically taking his first law and making it mathematical. And so what Newton's second law says is that an object's acceleration is proportional to the net force applied and inversely proportional to its mass. All right, there are some words here that we may recognize from our first unit on patterns. Proportional and inversely proportional. So let's think about what those mean. So when we say that the force is proportional, that the acceleration is proportional to the net force, what we mean by that is that the graph would look like this. In other words, that as the net force gets larger, the acceleration also gets larger. Let's think about that in real life. If I push something a little bit, it'll change its motion a little bit. But if I push something a lot, it'll change its motion a lot. And we know from our first unit that means that the acceleration would equal some constant times the net force. And that constant would actually be the slope of that line. All right, second half of Newton's second law is that the acceleration is inversely proportional to mass. So, inverse looks like this. So if I push an object with some force, let's say 10 newtons, if that object is small, it might change its acceleration a lot. But if that object is very heavy and we move down this way, then the acceleration will be very low. It's harder to accelerate a big, heavy object than it is to accelerate a small, lighter object. So this acceleration would be some constant over mass. And if we do this lab, what we actually end up finding is that overall, what's the acceleration? The acceleration equals net force over mass. Each of these things is the other one's constant. Now, this is a fine way to write this equation. You'll often find it written instead, because people hate fractions, as net force equals mass times acceleration. And this is one of those equations, kind of like E equals mc squared, that if you ever buy like a shirt with like nerdy science writing on it, it will almost certainly have this equation somewhere on the shirt. And it's just one of those equations that people like think of when they think of physics. All right, last of Newton's 3 laws is that for every force, there is an equal and opposite reaction force. And you've probably heard this one before. A lot of people don't put the word force in here. They say for every action, there's an equal and opposite reaction. But I think that makes it sound like it's about motion, and it's not. It's about forces. And this is one of Newton's laws that I think the most people know, but the fewest people understand or believe. And I think the best way to understand this is really through like a sentence diagram. So let's take a look at that. I am pulling on a box with a force of 10 newtons. All right. So I am pulling the box with a force of 10 newtons to the left. So what our third law tells us is that the exact opposite of this is also true. So let's identify what the exact opposite means. The exact opposite means the same two people or objects, so me and the box, the same amount of force, but the one thing that's different is the opposite direction. So let's think about what that would look like. The box is pulling me with a force of 10 newtons to the right. So again, what is that? It is the same two objects, the box and me, the same force, 10 newtons, and the opposite direction. Now, a lot of people just don't believe this. Like, no, it's not. I'm not moving. Well, it doesn't say that the box is the only force acting on you, and it doesn't say that you're moving. Think about if you were pulling a rope with a box attached to it. When you're done pulling the rope, if you look at your hands, they may be red or irritated. You may have blisters, and that is all evidence that, yes, the box was also pulling on you. However, your feet were also pushing against the ground, and that there was some friction there, so you're not going to move. And so there's lots of other forces too. But every force goes both ways. I think it's also important to realize that this applies, if we go all the way back to our initial thing, this applies to two different kinds of forces. And we're going to talk about two different kinds of forces in this class. The first are contact forces, which are the ones we've mostly talked about all through this class, where the objects touch each other. And honestly, most forces are contact forces. But it also applies to what we call field forces, which are forces that happen over a distance. And there's really two big field forces that you should know about. Gravity is one, and we're going to talk about gravity and the third law here in a moment. And then the other one is what we call Coulombic forces or electrostatic forces. And you're going to talk about those a lot in chemistry next year. All right, so let's think then about what does this look like if it's not a contact force, but if instead it's a field force. And gravity is one of our big ones. So we'll talk about gravity next week, but essentially gravity is a force that attracts any two objects with mass to one another. So gravity attracts any two objects with mass to one another. Yes, you and the person next to you have a force of gravity. You and a computer have a force of gravity. They are very, very tiny, and we will talk about that in January or February when we get to planetary gravity. Because usually what we see gravity as, and what we're going to really focus on gravity as in this particular unit, is that the Earth pulls on things on the Earth. And that is most of what gravity is. February, we'll talk about the other part of it. So in this case, I could say that the Earth pulls on me with a force of 800 newtons downward. So thinking about like our sentence diagramming here, our objects are the Earth and me. Our force is 800 newtons, and our direction is downward. So what does Newton's third law tell us? It tells us the opposite is also true. I pull on the Earth with a force of 800 newtons upward. And this is where people's disbelief really starts to settle in. Because we see, if I jump, I fall back down, right? We see the effects of Earth pulling me down. But we don't really see the effects of me pulling on Earth. So I want you to think, why is it that we see me accelerate, but we don't see the Earth accelerate? Okay, number one reason. I can think of three reasons, by the way. Number one reason. Earth's mass is huge. And we just learned in the second law that a large mass means a low acceleration. So even if I am pulling on the Earth with that force, once I divide it by the mass of the Earth, the acceleration would be so minuscule that we would just really not even be able to measure it. Second reason or third reason? Anybody have any other ideas? Yes, Claire.
I think it's hard to find something that we can observe relative for Earth's motion.
Yeah. I'm going to call this frame of reference. We are standing on Earth, which means it is really hard for us to see the motion of Earth. Just like when you're sitting in a car, you don't really perceive the car as moving, you perceive everything as moving around you. When you're standing on the Earth, you kind of perceive everything as like moving around the Earth. So even if the Earth were to accelerate upward a tiny amount, we probably wouldn't be able to like be conscious of it. All right, I have a third one, and I'm going to tell you that my clue is net force. Any ideas on this? That was middle schoolers.
No, those are lower school.
Oh, that's right. They come up for the bathroom. Third law or third reason, anything? Net force? Well, am I the only person on Earth?
No.
Okay, so I am pulling up on the Earth with a force of 800 newtons. That is true.
You were the only person on Earth to me, so.
Oh, I love you too, Straka. All right.
Boy.
But there are also billions of other people all over the Earth pulling on the Earth with a force of 800 newtons. And so it kind of all cancels out anyway. So why do we not see the Earth move? Any of these three is totally fine as a rationale, right? I am on the Earth, so I wouldn't see it move even if it did. The mass is huge, so the acceleration is going to be tiny. And hey, we're all canceling it out anyway. So why would it matter? But I am, back table, quiet. But I am pulling on the Earth with a force of 800 newtons, to be clear. So I'd say the third law is the one that the most people know and the fewest people really believe. But it's also incredibly important to a lot of things that we do day to day. So like walking is a third law thing because what happens, I push back on the floor and it pushes me forward. And that helps me move forward. All right. On Tuesday, we will do a lab to investigate these two relationships and see whether they really are proportional and inverse in real life and how close we can get to this being true in real life. And then we will start to learn more about other specific forces. Gravity, friction, springs are the big three that we're going to study. And we will also study two-dimensional forces and how those work. So that's kind of the next 3-ish weeks laid out. All right, any questions?